I'm sharing. I'm sharing a screen. Okay. Not sure how to do this. Let's just jump right in all the way. Okay, so what we've got here, this is my YakRover Onshape folder. And we've got a turtlebot here to talk about the kind of like CAD to simulation workflow using the various URDF and SDF and USD formats. But we're talking about the YakBot today, this little concept here. So I think for parts there was some missing context. You could look back in a certain thread in Discord. I was pushing the notion of like, what is the absolute bare metal simplest mechanical platform that could become the standard for everybody to kind of work off of for this project or other collaborators that wanted to come and be part of this project.
Right.
And there's a number of commercial platforms that subscribe to this sort of like two-wheel with a dragging tail concept, including one Anraj posted. There's actually, I think, Japan Space Agency or some, can correct me, but there's another like flight robot using this kind of general layout. One thing that's not shown here that would be a fun thing to maybe somebody else could do it in the Onshape model is this current config is just 2 motors with a drag tail, but you could loosely link together multiple nodes. So let's call the 2 wheels and the power compute kind of middle bar the atomic unit of this robot, and then you could link multiple together into a chain like a centipede, and then you have like sort of more interesting capability, and you could have 4-wheel, 6-wheel, 8-wheel. I think the robot that the other agency posted is 3 of these in a chain, with kind of like a slightly loose rotation limit constrained kind of skeletal joints. So there's like 3 of these links, and it forms a 6-wheeled robot made out of 3 nodes. Yeah. So anyway, the kind of base scaffolding is here. This model, I haven't made it public, but it's link shared, and I think it has edit permissions. I know Venkat did a Onshape tutorial a while ago. I don't know. Venkatesh, are you running professional or the standard or free? Which version are you running?
I'm running the free version, so yeah.
Oh, okay. It might be interesting to do a brief Onshape professional. So, yeah, this is the thing. There's a lot that you get with release management in Onshape professional that's pretty relevant to projects like this. All I'll say is if you all want to like get in on this model and edit it, just be copious about your branching and versions, because it's always easier to retroactively kind of pull things together and edit them, as long as that lineage is captured. So like before any activity, just make a version. It literally takes 2 seconds, and then that state will be captured here, and we can see what changed over time. And that just makes it very easy to kind of go fast and loose in 3D modeling. And that's really why I believe in Onshape as well. Like this is truly foundational versus a package like SolidWorks or CATIA. So cool. I'll just walk through the
question
briefly.
on that. If we do create a fork to explore either like adding some feature to your basic design or creating like a variant, for example, you mentioned the 6 or 8-wheeled version. So suppose I want to create like a version that is like a train carriage, like hookup thing. Or so variants versus building on features. What's the best practice here for doing either or both?
I mean, there's no right answer to do this, and the reason that I can prove that is if you ask any professional software developer how their organization handles branching and merging, there's no one answer. It varies a lot in terms of like, do people all work in the same daily repo and then branch on a version release, or do they branch for working purposes and merge in daily or hourly? And there's all different iterations and variations on that. And the beauty of Onshape is kind of all of that process and understanding can be used now for MCAD. So I generally don't have super strong opinions about how we do things. With my firm, I pretty much, if we have, like 3 or 4 people working on a project, I do like to have kind of a there's kind of 2 layers that I do. The first will be like a new variant or feature, and then each person, if they're going to work on something, there'll be like a working model. So, I could branch out this workspace and say this is like Yasha working. And this will get merged in on a very short time scale. So this will get merged back into the main line of that new thing we're working on, or all the way back into the main pretty often. And this is all just very important in Onshape, because usually you're going to be sharing. It depends. So usually you'll share like a version with somebody, or even internally, but it's really nice to be able to go to main and see, and just like see the latest thing. However, if somebody is like rattling around in main, it's going to be junk whenever you view it. So I try to leave main in a like relatively sane state. And then branching is where like the action can happen, just so that like it allows asynchronous viewing of the state of the model, especially if you're like in there rolling back the feature bar and updating things. It's nice to have like main being in a state that's like consumable.
It's
So
Is the
yeah,
version
how-
control in Git or something else?
what
Or
was
is
that?
their own? Is that version control? Is it done in Git, or is it their own thing?
Oh, this is all in the package. Yeah, this is
Okay.
completely air-gapped for many. I mean, internally it's probably Git, but
Okay.
like that's all under the hood. We don't get to see that, unfortunately. So I'm like creating let's call it a train. This is
Can
the
you-
Jackpot.
Can you have kind of diff between branches? Because
Absolutely. Absolutely. So check it out. So if we go into, I just created a new assembly called train. So it's like the YakBot train. Now, if I go in my tree here and I go into main, if I want to merge that in, it's going to give me this dialog, and it's going to ask me. I can even get pretty granular. This is a relatively new in the past few months. So I get pretty granular about which one I want to keep when I do this merge. And it shows me, unfortunately, it doesn't necessarily show you in this dialog exactly what changed. It'll just show you which documents, or in like the software world, files have changed. And it'll ask you if you want to preferentially merge one in. But Eric, to what you were saying, you can do this show changes in the branch tree. You can do the show changes here, and this will kind of give you a brief summary. So it'll say insert new tab assembly 1, and then rename that tab YakBot train. So that's like something that we can see. Again, this is why I just like make versions early and often, because you can be able to see what changed over time. If you don't, there'll be like a huge long list, and it gets very confusing. Very
Yeah.
confusing.
Okay, cool. Thank you.
Okay, and all this is part of the professional version. So since we will be on the free version and we access your model, we'll see these features, I guess, right?
This part, I'd actually have to log out of my business account, but this part, it should all be in the free one. The stuff that is not in the free one is this little triangle. So this triangle and the part numbering is not in the free one.
Okay.
Because all of the release, there's a release workflow, and then these part numbers are actually across my org. So like whenever I click this button, it increments a counter globally across anything that I'm working on or anybody in my org is working on. So like if I delete all these part numbers and click it again, it will re-increment these. And that's all part of like I've set up A to represent assembly and P to represent part, and this is all configurable stuff within my org. And like the number of digits, I'm only supporting like 999,000 part numbers, but haven't hit that yet. Need to go faster. So that the release workflows and the part numbering is a professional thing, professional and enterprise. But in terms of hygiene when doing branches and versions, that should be at the free tier. And yeah, that's like universally applicable. Okay, cool. So yeah, I think we were just gonna like model a little train here. So I think we're in, that's the subassembly. Let's call this the YakBot, like YakBot Atom. Okay, and then we'll go into the train. We'll insert an atom. And then we'll do a linear assembly linear pattern. Grab this guy. And I'm going to be lazy. I'm going to use it off the model. This is probably, I think the pitch is 200 millimeters. And that is currently locked in the document. I don't have a variable studio where I could link. Let me explain what I'm saying in a second. I'll just show you what I'm saying. I think we want more clearance than that. 303. Okay, so now we have a little robot train here. It's kind of cute. What was I blabbing on about the stuff? Oh, by the way, I don't know if anybody's noticed. So these tabs down on the bottom, don't look at those. You don't want to look down there. You want to click this the little magnifying glass in the lower right-hand corner. That gets you a nice ergonomic view of the tabs. So these are parity. The left thing with the magnifying glass, that's the same as the tabs. The tabs are just tiny and unreadable, and they should just delete them. I don't like the tabs. But yeah, this is like easier on your eyes. Use the left bar. It's good. Trust me. So if we look in how I built this model, I tend to be a very I mean, this is all just like a preference thing. I think when you're kind of building a new product or really going fast in rough prototype mode, it's okay to be much more of a fast, loose, direct modeler. And what I mean by direct modeler is like you make some features and then you like do a sketch on the side of that feature, or you even use direct modeling tools such as move face. So you're not even using a sketch anymore. You're like directly modeling the 3D. That's okay for prototypes. Eventually, though, you want to have a top level, like very top down sketch. So since this is such a simple design, and I just wanted it to be very configurable, I made this kind of like this is the one sketch to rule them all. So this controls everything. I also briefly put in this variable, which controls the overall dimension. So here, we're going to do a live test here. I'm going to take up the panel size to 300 and it might break everything. In theory, it should rebuild the main. Oh, look at that. Okay, so it sort of worked. Yeah. This is what I didn't change. So this is one thing that Onshape could do better. I actually might open a ticket with them to see if they'll add it. SolidWorks is better at showing you if this is a manually entered number, an equation, or a parametric equation. So if I double click this, it's going to show me that it's actually a variable. Okay, versus if I click the 50, that's just 50. So that's one thing they need to work on. We can't tell if this is driven by a variable or not, just at a glance. And this is consequential, right? Because some other person new to the project could come look in this sketch and think that it's just a dumb sort of like hard-coded dims when it's actually all parametric. So what might not be immediately obvious here is this one is a panel width variable. This one is a hard number, and that's a problem. So if we wanted it to be proportionally scaling, now this needs to be a panel width. Okay, so now that's the panel width. And then we want this to be some fraction. It was 50 over 200, which is a factor of 4. So we would want this to be panel width divided by 4. And now it's all proportional. And this should rebuild. Okay, it rebuilt. My little undulating wavy things. The little wavy guys down here didn't want to do it. I probably did some silly thing to model. Oh, yeah, it's some silly thing. We don't care about the wavy ones. That can be somebody else can add the waves back. Here, let's just kind of actually use, I don't think I've ever used the wrap feature. That was fun. I used the wrap feature to do that correctly. So let's just, we can kind of can kind of suppress those out. I should actually add these to a folder, waves. And now we can go ahead and suppress all that junk. Okay. So why are we doing all of this? So the power of what I just did is I cleaned up this model so that we can very rapidly iterate across different panel geometries. And this is nice because, for instance, if we want to do a spread of different variants, in terms of like a concept, what we could do here, we could go ahead and configure just that number. So we'll go ahead and configure the part studio. We'll call this the little bot, big bot. And now we're going to configure this number, the value there. And then this middle bot will be 100, 200, 250 maybe. And then this will be like a super big one for Venkatesh to go off-roading. And then so what you can see here, it already is, this is live. I don't know if you saw that. It automatically just recomputed everything. This is kind of a funny looking robot. So like, what is this thing? It's a little like sea creature. So that's the little bot. We now have this drop down configurations up here in the upper left. So now we can go to middle bot, it'll rebuild, and now I can go to big bot and rebuild again, and we'll have the big one. Oh, it lost its tail. Notice that the overall thickness hasn't increased, and that's intentional, right? Because a lot of our things like PCBs, compute batteries, all of that stuff is going to have a particular thickness that's characteristic that we want to stay fixed. Same thing with the shafts of the motors. Let's say we have the same motors, which probably wouldn't be the case, but this little core here is staying the same diameter because that was intentionally not made to be a proportional variable in the geometry. So we go down to the little bot, it has the same core here and also the wall thickness. Anyway, so this is just me doing some live on shape here. Let's talk about actually filling this with parts. So this was really just a concept. Can people see my camera? This is, I think I mentioned before, this is a power bank, a USB power bank that I got as free swag at some industry conference. I don't even remember. But this was kind of like the core premise is just take this and put some brain and actuation on it. So, you know, if we take the solar power bank, that's power and power storage. So power source and power storage is solved. We put motors on it, locomotion is solved. We put compute on it, the compute is solved. Now we have a platform. The thing that we're missing from this platform is a mission. That mission is going to drive the overall dimension here. So the mission is going to drive if we have the big bot, little bot, you know, which one we would.
I'm sorry, can you say that again? Did I understand you to say that your design really has only one parameter and the mission can help decide what the value of that parameter is?
Yes, and certainly there could be, this could very easily be multivariate. This is just a one critical dimension that I've made the overall geometry rebuild off of.
Mm-hmm.
Because I mean, you know, at the end of the day, all products do have kind of a critical dimension. You know, a car has a certain dimension, a model car has a certain dimension, and all of that is proportional to the payload. The payload is a human in one versus a mouse in the other versus like like a, you know, a train can be a whole thing. But that dimension is going to be driven by something like, for instance, if there's a certain payload that we need to carry that has some governing specification, like a governing specification in a payload could be its power. So it needs a minimum amount of power. Then we need a minimum area of solar panel, and that selects our robot size. It could also be its actual physical dimensions. Let's say it's a science experiment that needs to shoot a laser a long distance. So it needs to shoot a laser over a meter, and we don't want to bend that laser more than 3 times with mirrors. So we have to have a robot that's at minimum 0.3 meters. Well, I guess if you bent it 3 times, it'd be 4, so it'd be 0.25 meters.
The battery bank you showed that you got the free sample of, what's the parameters on that? Like how much charge does it hold, and how long does it take to recharge based on the panel size? Are those specs out?
I can read you what the silkscreen says. I don't know if that's going to be accurate, but I'll read you what it says. So this says 2000 mAh. I'm going to assume that's a single cell in series. It doesn't specify that. So I'm going to assume that's 3.7 to 4.2 volts at 2000 milliamp hours. It says the solar charging. This also, this could mean a lot of different things, but the solar charging spec is 5 volts at 200 milliamps. And I'm going to assume that that is provided at full noon sun at the equator, right? That's like the 1 kW per square meter irradiance level. So depending on your latitude, I don't even know. I think California is between, I don't know, like 25 and 35 degrees. I don't even know. It's a good question. Somebody could look that up. So if we're going to Mojave, we have a loss factor because the sun's at an angle, depending on the season as well, where we have to derate all of that. And then we start to get our baseline power budget, depending on the season, depending on where it's deployed, etc.
Okay. So wait, the charging is 200 milliamps, assuming an equator or whatever, and the capacity is 2000 milliamp hour. So wait, does that mean it charges in?
Well, this
how
is
long
okay.
does it
So
time to charge from that, from 0 to full.
this should be wait, what?
I would guess it takes 10 hours to charge.
Oh, I think it got, no, it did know A correctly. There we go. Okay. It's like, come on. It's like H is like the Higgs. No, I forget what that constant is, but Google is trying to be a better physicist than me. So okay.
It's a Planck constant,
Planck's
right?
constant, yeah.
Yeah, which constant is it again?
Planck.
Yeah, the Planck's yeah, that's right, Planck constant. Okay, so there's your dumb answer. Okay. We say 5 volts at 200 milliamps. So we say 5 volts times 200 milliamp times, I'm going to say a shading factor conservatively of 0.5. And then I'm going to say we get 8 hours of that.
Okay, and I think you wanted 200, not 100. Okay.
Okay, we get 2 watt hours per day. And we got a 7.5 watt hour battery. So if you sit there and do nothing, you gotta wait 4 days to fill your pack.
Okay. So that gives us an idea. And if we, the biggest drain would be whatever motor you pick, right? So, and it would have to be typically like a 6-volt motor minimum. And so you'd be upregulating the voltage.
So this is what I'd say. I mean, there's a few things you're fighting. So the first thing that you're fighting in a product like this is the quiescent draw. So the quiescent draw is something that, it's like your fixed cost. It's something that you don't have much. Does everybody understand the notion of quiescent current, quiescent draw? It's just the notion that there are certain components in the design which consume power always. So it's like when the device is sitting idle or sitting completely off, it is consuming energy because the battery is connected to something always in a product such as this. So the quiescent draw is the big penalty you're paying. So that's where you get into something like, let's say we're using a Raspberry Pi, which I don't know that I would suggest to do something like that here, but you could use Raspberry Pi. I actually I could measure it. I don't know what the quiescent draw of a Raspberry Pi is connected to USB power. It's going to be some non-zero number. That would be the first thing we would have to scratch our heads over, is like, is that quiescent draw acceptable? Or would we need to take mitigation measures up to and including putting the Raspberry Pi on a switched power supply that we would then control by another little microcontroller that had lower quiescent power characteristics. So we would only turn the brain on when we needed, to think really hard. But if we didn't need to think very hard, we could use the little lizard brain sort of microcontroller to do low-level power management tasks and housekeeping at very, very, very low power and quiescent draw, versus the RPi, which we would only turn on for batch compute workloads, or when we had excess power when the sun was out. The motors we also have complete control over. So the motors have 0 quiescent draw, which is great. We only have to fire those up when we gotta like do some locomotion. But the locomotion is also a function of the mission. Like if, for instance, I think the example application I laid out was measuring radiation. I think that's the governing factor then, is like, how often do you need to move to take a sample? Maybe it's often, maybe it's not. I think radiation is interesting because it's very, debatably low spatial resolution. So we'd probably want a robot that could actually move pretty fast if we were doing a mapping that kind of a metric, versus if you were mapping something else, like I don't know, maybe some kind of lithium content or nutrient, some kind of other surface measurement property. Maybe that's at the meter level, or decimeter level, versus tens of meters, 100 or kilometer level. Does that make sense? So there's definitely this open question of the mission.
Yep.
Yeah. So what's the trade-off? The trade-off for doing a smaller reptilian brain plus a bigger brain. The trade-off there is I guess just space. Otherwise, why wouldn't you always do that?
Not space, but power is usually. But what do you mean?
Like why not? Why? It seems like that would be like the solution you would want always, to have like a smaller device, a small microcontroller with lower quiescent draw controlling the larger one. But you're saying there's a power requirement.
I mean, at the end of the day, it's simpler, right? Like fewer stuff. So if you can get away with a big brain and you got power for a big brain, you don't have to deal with the overhead associated with handing off power, starting, restarting.
Right. Okay.
Dealing with connectivity to the little brain. Like sometimes it can be your whole comms stack was intended to run on Linux. Oh, now you're running it on a little teeny thing. So now you have to have a different stack.
Right.
But there are projects like Zephyr these days that try to solve that problem, where they're like, you can bring whatever you want and it'll just run. And we've got like drivers and a build system for that. But these are all sort of decisions one has to make early in the game, because otherwise you can be kind of stuck. This isn't interesting. What am I looking at? I was going to look for. This is the vehicle bone.
My real limited research on the Raspberry Pi Zero, which is kind of a smaller less powered one, which I have on my rover, says that it would use under load, it could use 1 watt. So that would be like half the daytime running consumption of power.
Yeah.
Ton your
So
load or some load.
this is a good task for somebody else to do, as an example of like a work product chunk. Is this question of like, how sophisticated does the stack need to be, and how big of a brain can support the execution of that stack or of the workload that the stack is going to have? Because in my experience, the Raspberry Pi Zero is kind of garbage. Like, it's just so underpowered. Like, if you want to do ROS stuff on that thing, it's got, I don't even think it has is it 512 of RAM or 256? Okay, it's got 512. The Zero 2, this one has a little bit more punch, but it's still 512 megs, which is like brutal. I mean, I don't know if you try to run ROS on that thing, but I have to add like 4 gigs of swap on the SD card, which is even more brutal. It's just brutal times brutal to do ROS on a Raspberry Pi Zero 2.
I was unable to run local development tools on it to like live code with like VS Studio or VS Code or whatever. So yeah, it hits that RAM limit real easy.
So I was gonna mention, I haven't done any projects either personally or professionally with these little ones, but they've been on my radar for a long time. They're kind of, I don't know, people have mixed feelings about them. The nice thing about this is, one, it's got 4 gigs. You can like 4 gigs has room for activities. There's a lot of stuff you can do with 4 gigs. The next thing that's nice about this little guy. Oh, here's a little benchmark next to other Odroids, not Raspberry Pi. That's lame. Oh, that's the other one I wanted to mention. So the first perk is we got 4 gigs, room for activities. The second one is we have this letter K. It's the eMMC riser, and the I/O performance of the eMMC is like 3x that of even a high performance SD card. I don't think they list it here, but that's nice. So you get like way better RAM and write to disk with this little one, as an example. In terms of like the compute per watt, you know, they do some benchmarks here. Like, yeah, it uses a lot of power. Like, there's no debating that. This thing even uses 200 milliwatts off. Like, that's some serious quiescent draw. So remember we did this calculation here. So this is 2 watt hours per day. And then if we do 0.2 watt times 24 hours, we can do the mental math. So this little portable power bank, it generates 2 watt hours per day. That Odroid, when it's off, uses 5 watt hours a day. So right there, you're dead. You didn't move. Your rover is completely dead, because when the Odroid is off, it's using all the available energy. But if we put the Odroid on, again, a little switch and only fired it up now and then, you could potentially get by, because you could just budget your joules appropriately. Or you could come over here and say, nope, need the big bot. And then we have a much more respectable energy budget. Does that make sense? But this is something that somebody could look at and check out. There's also a new, oh, that's a big, it's a lot of stuff. The other thing that we're going to encounter if you actually want to send this to the desert, upper temp limit. Don't quote me on this, but I believe usually in a personal computer, these days, the limiting factor on the upper temp limit, assuming that you have the processor like with a big enough heatsink, so the processor aside, is going to be the RAM. So the RAM is going to start to sweat, and you're going to need to buy a high temp limit RAM. So you can get RAM that'll go up to like, I think 85C, like high temper. Wide temp. So this is a -40. This is not EC. Oh, this is ECC. Okay, so this is ECC wide temp. Whoa, it'll even. Wait, what is this lower refresh period at 95 centigrade? The point is, a lot of these boards have RAM soldered to the board, which could be a problem. So then you have to look at slotted boards, which this is not slotted. This is all soldered on. So unless you want to rework the RAM module, I would not recommend that. It's a lot. It's pain. So if we come over here, this is slotted, so you could actually put in a wide temp SODIMM if that becomes a limiting factor for a higher temp.
Joshua, isn't it more resistant to knocking around if you don't use slotted, if you use built-in?
That's a loaded it's a loaded question. Generally yes. However, there can be other factors in that question. So one of the common things that we do to harden boards to make them more resistant to NVH, noise, vibration, harshness, is underfill, which is like BGA. I don't know if Odroid underfills their stuff. So it's where you actually solder down the chip, but then you use a very, very low viscosity adhesive and you let it kind of flow under the chip. And that literally bonds the chip to the board in addition to the solder. So this is what you do in any sort of application where you're concerned about drop testing in a consumer product or an automotive. But I don't, because Odroid is sort of a kind of hobby grade thing. I have no idea if they underfill. But we could ask them, or we could ask them to do it, or we could even DIY. We could do our own underfill, maybe. We could underfill the boards, harden them out. So there's a lot of options there.
But again, it will depend on what to do, basically, right? Because I guess this epoxy treatment has a smaller range than a slotted choice, no?
Yeah. So in general, slotted is going to be more troublesome in shaky environments versus it just being on one board. But I'm just saying that there are other finer considerations, even if it is all on one board. You can also certainly, because there's actually at the board scale, and that's all assuming that. So you have to remember, for a product like a cell phone, there's no volume to like suspend the phone against or dampen it against vibration. In this robot, there's going to be plenty of opportunity to like shock mount PCB. So you could have some kind of superstructure around the compute that's going to help it deal with the peak shocks. But in something like consumer product, very often there's no room for any of that crumple zone or shock mounting. So you just have to assume that it's going to get dropped and that it has to deal with being dropped. So this is where, you have these mitigations come in to harden out the product robustness. But anyway, so in terms of this design, there's the power budget question, and then that will directly impact the system architecture, because like this is a good example of, depending on the compute, how much is Raspberry Pi's quiescent current?
I thought it was 0. You know, I leave my robot off and still has power afterwards.
Does that disconnect the battery, or what does off mean?
No, here it says on the bottom, when you power off a Raspberry Pi, any model typically use 20 to 30 milliamperes until you physically disconnect the power.
Correct.
So it could be that this system I have physically disconnects the power. I don't know. But you can see the number, 20 milliamp, 0.1 watts.
So here's a good 0.1 watts. That's an insane amount of power. That's so much power. So I'll give you an example. This is a off-the-shelf module we use from a company called Blues Wireless. Pretty cool company. So they make that little cellular modem that makes it easy to build your product and get going. But it's really designed around low power, and their modem, when it's off, uses about 5 microamps. So 5 millionths of an amp. And then you multiply that by the battery voltage, which is, let's say it's 4 volts. So 4 times 4 microamps, 4 volts times 4 microamps is like 16, let's say 20 microwatts, which is 0.00002 versus 0.1. So that's kind of the difference that you have with these little single board computers. So yeah, Raspberry Pi directly connected to solar panel power manager is just a no-go. There has to be some kind of intermediate thing, but it also depends on the mission, right? Because to be fair, if you're talking about sort of like a beam robotics as simple as possible, kind of the brutal way to do this is just have the computer turn on when there's enough power and there's no battery. And then when the sun goes down, the robot also goes down. And it's sort of this directly coupled to nature, not fighting against nature approach to the system. So that's one way to do it. In terms of carrying out a mission, that's another thing. It's like, is the mission constraint? It has to be able to operate outside of daylight hours. Let's say you're interested in measuring something that only happens at night. You need to store your energy. But yeah, I don't know. For this, I was kind of thinking, let's talk about just like the simplest way to do this. So we would need to have, I think I would suggest actually having a little custom power manager board that would have a little brain, such as some microcontroller on it, that would deal with turning on the big brain. So the power manager board would have its own controller and firmware. And then that would have the ability to switch on a bigger brain. So we would use off-the-shelf big brain, custom little lizard brain, and then as off-the-shelf as possible, motor solar panel. Whole thing is additively manufactured. Now, you might say, oh, how can you ship PLA to the desert? Well, we wouldn't make this out of PLA. It's like, oh, well, ABS and so. Well, there's a lot of materials out there that we could conceivably use. Now, some of them would probably be literally more expensive than metal to produce, but Let's see. Yeah. So a lot of grades of Ultem will do 300 Fahrenheit. What's 300? Yeah. So like 150 centigrade. This plastic will deal with the desert all day long. This would be a very expensive part to print, but we could. And so you could just print these little robots out of Ultem or whatever material that achieves adequate performance for direct use. But yeah, that'd be a really simple, very simple robot at the end of the day.
Well, one question, maybe you talked about it already. So how do you choose the length of the tail? You know, we can see the tail here, but I guess the length depends on the several factors.
The other, let's actually update. So I'm going to do another version here.
So when we spoke, Yasha, you mentioned, I think, an interesting insight that the longer the tail, the lower the contact force, so the less drag you have to provide the counter torque. So that seems to me like a trade-off between drag friction from dragging the tail on the ground versus the length penalty of like just making the whole thing bigger. So that seems to be the main trade-off.
Yes. So there's always, you're between a rock and a hard place. So the tail getting longer makes turning harder because you have to drag the tail along the ground as it's turning. But it does decrease the amount of force, like counter torque, that you have. This was the reference robot. Let's turn this off. So we can see this little robot pulling around. Oh, there's a little rabbit it scared away. So this little robot has a pretty short tail, actually. I'm hoping they'll show some footage of it going sideways so we can kind of see better. Yeah, so here we can see, maybe this will be easier to view. So the tail is actually almost within the wheel diameter in their design. So it's very short. And as for the rationale for that, I don't know. Maybe it becomes more obvious in the field testing. So, you know, we go in here and we say, I need to make this. Oh, I didn't fully define this sketch. So let's say the tail must be shorter. So we'll do, again, we'll divide it by 2. Let's say 1.5. We'll just a little bit shorter. Yikes.
You know, another big difference in the geometry between that is like, it looks like theirs is very weighted in the rear, like to one side. The way the chassis is asymmetrical as opposed to being symmetrical.
Yeah.
Like, does the tail need to be heavy to provide the
No.
counterpart?
Here, let me just
The tail is going to be pushed into the ground by the counter torque of the motor, so it doesn't actually need to be super heavy. In fact, heavy is, I think, bad because that will increase the contact friction. The other consideration is when the two wheels are moving in opposite directions for turning, imagine the torques cancel out, so the tail is basically resting very lightly on the ground, but it's turning, so it'll be dragged sideways and could run into obstacles. So when it's moving forward, it needs like no space, it's narrow. But moving sideways, it could hit things, unless, of course, it's within the wheel diameter itself. But otherwise, the tail will hit things, I think. But it is almost 10 minutes over, so this might be a good place to stop and pick up in the next session. I started putting together a spreadsheet based on what you were describing, Yasha. So I linked that in the comments. Let me just quickly flash that here, just so maybe we can talk about it for a minute before.
How is this format? Is this interesting or?
I thought this was great.
Yeah, I think this is how we should do as much work as possible. But yeah, I started capturing this, and I think the obvious next step is to like work out this overall system design and then see how we can break it up into pieces that each of us can take on, something like that, right? Is this a good sort of format to work out the overall system design? So yeah, this is editable by all of us, so have at it.
I would still push this notion of, again, not getting completely married to it, but this general notion of a mission or maybe a couple different missions that could be kind of the North Star.
Yeah, let's actually schedule that for next week as well. So there's a systems tab and there's a mission tab, and I don't know how to parameterize the mission, but it's probably things like duration, terrain, all these sort of environmental parameters that sort of like shape the mission. And then the options like, are we measuring radioactivity or something like that? So yeah, I think between these two, next session, the output should be bits of things that we can each take on. So like, for example, if the little lizard brain plus main board is one well-defined pair of things, one person can take that on, that type of thing.
Cool.
All right.
Sounds good.
We need to talk about census as well, because otherwise we have no IO basically with the world.
Yeah.
If it's in the desert, we'll also need location, right? GPS, because if it wanders off in like a random
Yes.
pattern to measure radioactivity, we have to go pick it up again somewhere. So yeah, a bunch of other things we need to work out next week, I think. Or how do we want to do this? Do we want to try the modularity direction, which Mayor wanted? Oh, Mayor jumped off. Or is he still here? Let's see. Oh, Mayor's no longer here. Okay, yeah, let's discuss that offline in the Discord, whether we do this next week or the week after. So we were going to try 2 parallel paths at once.
Yes.
All right,
Great.
yeah, this was great.
Thanks, everyone.
Yeah, thank you.
Bye.
Rick, bye.